Okay, so we are in causal inference in statistics, this book right here. And we're in chapter 1 still, question 1.3.9. Okay, and this is a two-parter, A and B, so we'll look at them in turn. So, for part A, we want to prove equation 1.22, which is right here, using what they call the orthogonality principle, and we'll touch on that. And then we're given a hint, which is equation 1.26 in the book, which is right there. Okay, so first of all, what is the orthogonality principle? The orthogonality principle states that if we're running normal linear regression, so on an outcome variable y with predictors x1 through xk, that the best coefficients, here represented by r, if we're using least squares, is obtained when epsilon, the error term in our regression, is not correlated with any of the x variables, predictor variables. Okay, so I'm going to touch on that at the end of this first part of the question, but for right now, just take it as that being a true fact. So what are we being asked to do? So I take what we're being asked to do to say, assume that the orthogonality principle is true, which is what we just stated. Find B, the coefficient that's given up here, for normal linear regression with a single explanatory variable. Okay, so I'll show you how I went about deriving this, but I will say that there are maybe more intuitive ways to derive this, but I'm just going by kind of the instructions that were given in the book. Okay, so we start with our linear regression, which is right here. And if we take the expectation of this, so these steps are more or less outlined in the book around equation 1.25, 1.26. So that's kind of where I'm taking these steps from. Like I said, I would not do it this way normally, or just left to my own devices. But so we take the expectation of y, and that equals the expectation of the right-hand side of the equation, which can break down to the expectation of a plus the expectation of bx plus the expectation of epsilon, again, which is the error. Okay. So now we can simplify this, the expectation operator. We can make some simplifications with the expectation operator, and also with the fact that in normal linear regression, the expectation of epsilon of the error is 0. That's just an assumption of using least squares. Okay, so if we do all that, we get that the expectation of y is a. Why? Because a and b are constants that we're trying to find. But whenever I have a constant, the expectation of the constant is just a constant. So the expectation of a equals a. Okay. And similarly, here, the expectation of bx is b times the expectation of x, because b is a constant. And again, the expectation of our error is 0, so we can simplify all of that to this. Okay, a plus b times the expectation of x. Okay, so now we're going to follow the hint, okay, that was given in the question here. And we're going to multiply everything by x, and then take the expectation. Okay, so now I multiply my linear regression by x. Everything gets multiplied by x, so I have xy plus ax plus bxx, which is bx squared, plus x epsilon. I take the expectation of all of that. Okay, now I can simplify this again using those same rules, right? The constants can pop out. And then the orthogonality principle says that the expectation of x times epsilon should be 0, right? Because the expectation, well, because they're uncorrelated, right? So the expectation of the error is going to be 0, and so it doesn't matter what it's being multiplied by the x. Eventually, all of that should go to 0. Okay, so that equation just simplifies to this here. Okay. And so now we have two unknowns, a and b, but we have two equations. That was the whole reason that we multiplied everything by x and went through. Okay. So we have two equations, two unknowns, and now we can go about solving them. So quickly, I can just get the a, or a in terms of b, which isn't all that helpful, but that's okay. So I get this. and then I get B in terms of A. All right. And so what we're trying to find is B here. All right. We're trying to find the X, or we're trying to, well, in fact, not find an expression for B. We're actually trying to show that B equals this, the covariance of XY divided by the variance of X. Okay. So you can go through my steps here. I don't think it will be helpful for me to go through every single step. But let me see if there's anything in here worth mentioning. I don't think so. I think that the steps are pretty straightforward. But eventually what you come out with is this expression. Well, this top expression is just the definition of the covariance, and this one is just the definition of the variance of X. Okay. So now let me go back to the orthogonality principle, because again, the orthogonality principle says that when epsilon is uncorrelated with any of the predictor variables, we get the best coefficients, the least square coefficients. But it's not really clear what best is supposed to mean here. So I want to clarify what that means. Okay. By best, let me back up just a little bit. So let's go. Let's do what we just did, but now we're not going to assume that the expectation of X epsilon is 0. In other words, X and epsilon are correlated in some way. Okay. So I'm not going to go through all of the steps, but we get, when we pool our equations, we get these equations right here. Okay. Where I'm using A prime and B prime to signify that we have that these are different estimators, right? Because the expectation of X epsilon is no longer 0. Okay, and so we get these two equations, and then I can solve them both for A or in terms of A prime and B prime. Notice that A prime looks very much like A, and the reason is because we're still assuming that the expectation of the error is still 0. So that drops to that. Okay. So when you go through all the steps, what you end up with is that beta prime equals this. Okay, so we have this little tag-along term here. Okay. So what is meant by best? Is B better than B prime? So by best, I believe what the authors mean to imply is that whereas B is unbiased, B prime can be biased, and so it can be biased when this term right here is not 0. Okay, and so so now what do we mean by bias? So first, let me say that so I'm going above and beyond the question here, and so I'm not going to give it a whole lot of explanation. But if you want more explanation, you should go to Ben Lambert's YouTube page and check out his econometrics playlist. And it's a very long playlist. In fact, it has to be broken out into 2 or 3 different playlists because there's so many videos. But if you go to the one that has the link here and you just kind of look around for omitted variable or omitted variable bias or even Gauss-Markov conditions, you will find a better explanation than what I will provide here. But roughly, what this is why beta prime is going to be biased. Okay. So if the expectation of X epsilon is not 0, so in other words, we have beta hat is beta with the addition of this other term here. Okay. Then what it implies is that our regression, right, we thought that our regression was y equals, we thought that it was this, but it implies that there is another term hidden in the epsilon term here, okay? And we could write that, so there, in other words, there's another variable that we just did not take into account, and we'll call it x2, and we could write that, we could and should write that as another term in our regression equation, b2 x2, like this. Okay. Now, because we omitted it, well, okay, let me back up one more time. Now, if we are interpreting our b coefficients as the causal effect of the variable, so in other words, if I'm saying that b is the causal effect of x on y, right? well, then that means that there's a whole nother cause of y, or contributing factor to y, that we are not accounting for. Okay? And so now, if x, the variable that we are accounting for, and x2, the variable we are not accounting for, are related, well, the impact of x2 in the real world is still affecting y, even though our regression is not capturing it. So what our regression will do is the impact of x2 will be absorbed into the b coefficient to the extent that x and x2 are related. Okay? So, and so that relation between x and x2, that is the correlation between x and epsilon, right? Because x2, again, remember, it's an epsilon. Okay? So if we run our regression and we think that that b represents the effect of x on y, but unbeknownst to us, there is actually a b2 x2 that is not being accounted for, and some of that impact gets absorbed by b, then what b really is b prime, and b prime is the effect of x and some effect of x2 on y, right? I hope that makes sense. Okay, so in other words, it leads to a bias. It means that beta hat is no longer representing the causal effect of x on y. It's representing the effect of x and some other variable or set of variables on y. Okay. That was a mouthful. Okay, so now luckily part B is kind of quick. So we're just meant to calculate all of these partial regression coefficients. Again, these are coefficients where a variable has been controlled for, right? This is what multiple regression does, right? So we might have the effect of x on y holding z constant, okay? And it just so happens that when we run linear regression, multiple linear regression, these are the coefficients that we come out with. So it's presented here, but normally when you learn about these things, it's not, well, you very quickly gloss over this type of notation. But anyway, so these beta coefficients, here's the formula for it, okay? So anyway, I'm not going to go through all of the steps, okay? But we're supposed to take the sample from study question 1.38. I think that the text is 1.37, but it should be 1.38. And we're just going to plug and chug the values for everything here, okay? So when you go through and do this, I've done all the math, but this is what it should look like. Okay, that's it.